that I did yesterday, but you should be able to follow what I'm trying to tell you today, even if you didn't see what was going on yesterday. But as a reminder, yesterday I talked in the end about how we can generate pure spin currents via electrical injections in devices that look like this, where we pass an electric current through the left-hand side, and they generate a spin current that flows to the right-hand side. We can measure it electrically by switching the magnetization. If you were there yesterday, I hope what you took away from this is that this is a very nice way of generating a pure spin current that is well defined, and that it's a very nice way then to characterize spin relaxation in great detail. For example, yesterday I demonstrated how by looking at the temperature dependence, you can look at different contributions to the spin relaxation and see what comes from the bulk, what comes from the surfaces. So today I want to essentially address two questions. One is, do we actually need ferromagnets in order to generate spin currents? And the answer is no, not necessarily, and you'll see that. And the other question is, do we need electric currents to generate spin currents? And again, the answer is no, we can do it without, and I'll demonstrate that. So let's focus first on the first one. How about spin currents without ferromagnets? Well, so yesterday when I talked about electrical injection, we would get a spin current because electric currents in a ferromagnet are automatically spin polarized. And if you then pass the current from the ferromagnet into a non-magnetic material, this polarization is maintained to some extent. And that's how you can generate the spin current in a non-magnetic material. But can you do something even without having any ferromagnets? And the answer is yes. In fact, already in the 70s, in 1971, there was these two guys, Diakonov and Perel, in the Soviet Union at the time, that predicted that if you pass a current through a material, if you have a spin-dependent scattering, meaning that spin-up electrons scatter differently than spin-down electrons, then by passing a current through this material, you can generate a transverse charge current, transverse spin current. It's kind of like this. So if you have your current going through a non-magnetic material, and if spin-up scatters preferentially to the right and spin-down scatters preferentially to the left, then they will accumulate at these edges. And it was interesting, there were actually in the 80s a couple of experiments along those lines, but then this idea got mostly forgotten. And then in the late 90s, incidentally, this was at the same time when I was in San Diego, there was another guy